Here V is a Euclidean space upon which the inner product function this is defined, and alpha beta are any two vectors from V. Alpha beta are any two vectors from V. You have to check whether this relation is true or false, or otherwise you have to prove this relation. Rather to check, you have to prove this relation, that norm alpha plus beta whole square plus norm alpha minus beta whole square, this is equal to 2 into norm alpha square plus 2 into norm beta square. Alpha plus beta, here we have considered the norm vector of alpha plus beta. You all know how to compose or add two vectors. Alpha plus beta means the component wise addition of these two vectors, alpha and beta. Similarly, alpha minus beta means the component wise subtraction of these two vectors. And we have considered this, the norm of this vector alpha plus beta, that means norm alpha plus beta whole square here, and similarly here norm alpha minus beta whole square. And you have to show this is equal to 2 into norm alpha square plus 2 into norm beta square, where alpha beta are any two vectors from V. V is a Euclidean space. This is the inner product function. So let us now start how to prove it. First, we have calculated norm alpha plus beta whole square. According to the definition of norm alpha plus beta whole square, this is equal to inner product of alpha plus beta comma alpha plus beta, inner product, functional value under the inner product function of this ordered pair vector alpha plus beta comma alpha plus beta. As previous problem, as we have done in our previous problem, we have expanded this alpha plus beta comma alpha plus beta. This is first component vector alpha, this is a first component vector alpha, and for this we have written this alpha comma alpha. This is the second component vector beta. For this first component vector alpha we have written beta comma alpha. For this first component vector alpha and this second component vector beta we have written alpha comma beta. For this second component vector beta and for this second component vector beta we have written beta comma beta. So let us now see again what we have done here. For this first component vector alpha and this first component vector alpha we have written this alpha comma alpha. For this second component vector beta and this first component vector alpha we have written this beta comma alpha. For this second component, for this first component vector alpha and this second component vector beta we have written alpha comma beta. For this second component vector beta and this second component vector beta we have written beta comma beta. And according to the definition of alpha comma alpha, this is equal to norm alpha square. And for this, similarly, for this vector beta comma alpha, norm beta square. As the inner product function is symmetric, that means the value of alpha comma beta is equal to the value, functional value under the inner product function of beta comma alpha. So alpha comma beta equal to beta comma alpha. So what would be for these two? We have written for these two 2 into alpha comma beta. So this has become as norm alpha square plus 2 alpha comma beta plus norm beta vector square. Similarly, we are calculating norm alpha minus beta vector square. So norm alpha minus beta vector square, according to the definition, we can write this is equal to alpha minus beta comma alpha minus beta. And as we have expanded in this case, similarly we have expanded this. alpha minus beta comma alpha minus beta. For this first component alpha and for this first component alpha we have written alpha comma alpha. For this second component vector minus beta and for this first component vector alpha we have written minus beta comma alpha, because here is one minus side, minus beta vector, minus we have taken outside this parenthesis. So minus beta comma alpha equal to minus beta comma alpha. And for this first component vector alpha and this second component vector minus beta we have written minus alpha comma beta. So this minus we have taken outside this parenthesis. So for this alpha vector and minus beta vector we have written minus alpha comma beta vector. And similarly for this second component vector minus beta and for this second component vector minus beta we have written plus beta comma beta, because these both vectors contains a minus radical minus sign. And we have taken common for both these two vectors, so this will be minus into minus plus, so plus beta comma beta vector. And according to the definition of a norm alpha, alpha comma alpha, this equal to norm alpha square, beta comma beta, this is equal to norm beta square. And as we know, the inner product function satisfies the symmetry property, that means alpha comma beta equal to beta comma alpha. So minus beta comma alpha and minus alpha comma beta, in place of this we can write minus 2 alpha comma beta. So this has become norm alpha square minus 2 alpha comma beta plus norm beta square. Now we shall add these two, norm alpha plus beta whole square plus norm alpha minus beta whole square. We have done here. So norm alpha plus beta whole square plus norm alpha minus beta whole square, this is equal to, for this portion norm alpha plus beta whole square portion, this is equal to norm alpha square plus 2 alpha comma beta plus norm beta square. We have written here norm alpha square plus 2 alpha comma beta plus norm beta square. This is for norm alpha plus beta whole square. And for this second part, norm alpha minus beta whole square, this is equal to norm alpha square minus 2 alpha beta plus norm beta square. And we have written this here, norm alpha square minus 2 alpha comma beta plus norm beta square. Now we have calculated. This is a plus 2 alpha comma beta and this is minus 2 alpha comma beta. Alpha comma beta means the functional value under the inner product function. That means these are two real numbers. So plus and minus, these will be omitted. And alpha, norm alpha square, norm alpha square. This is 2 norm alpha square. And similarly norm beta square plus norm beta square. This is equal to 2 norm alpha square plus 2 norm beta square. So what we have had, norm alpha plus beta whole square plus norm alpha minus beta whole square, this is equal to 2 norm alpha square plus 2 norm beta square. This is the relation. This is the relation, this. So the proof is complete. Okay.